Hello everyone. In this video I'm going to discuss about transformation from time domain to frequency domain. I will use 3D graph to describe how the transformation of from time domain to frequency domain. So this graph will contain of amplitude. This axis, amplitude axis, and this is time axis. Okay, if we look from here, what we can see is amplitude versus time. So we have three signal. Let's say signal number 1, frequency 1, signal number 2, frequency 2, and also signal number 3, frequency 3, with a different amplitude. So what we can see from this view, we can look here. This is a combination of signal number 1, signal frequency 2, and also signal number frequency 3 is combined, all combined together, and will become one signal. Combination of all three frequency will become this signal. This is we call time domain view, or we can say that time domain signal. Okay. Next is frequency domain. Frequency domain. If we let's view from here. Is our eyes. When we look from here, what we can see is this is the signal for signal number 1, frequency 1, signal number 2, frequency 2, and signal number 3, frequency 3. This is signal strength of 3 signal. So we have 3 signal separately shown in frequency domain. Okay. Now, how to transfer from time domain to frequency domain? Okay. To transform time domain signal into frequency domain signal, we need Euler formula. Euler formula. Formula is equal to E j theta is equal to cos theta plus j sin theta. Okay. Our time domain signal is equal to ft. Now we want to transfer to frequency domain. Frequency domain is equal to f omega. Alright. So we divide time domain signal divide by the Euler formula is j omega. Then we rewrite it. I think this one we can rewrite, become ft minus f times e minus j omega. And then we know that our signal is start from minus infinity to infinity. Okay, our time is from minus infinity to infinity. So we integrate from minus infinity to infinity d omega t. Right? So we don't t respect to times. So this is the formula to convert from time domain to frequency domain. Okay, this formula is equal to f omega. Okay, this formula is called Fourier Transform. Right, this is general formula for Fourier Transform. F omega is equal to integration from minus infinity to infinity. Our time domain signal. This is our time domain. This time domain equation for time domain function. T amplitude. This one is sinus waveform. So with time is sinus waveform. Let's waveform cos and sine waveform. Okay, this one is sine waveform. So we will get Fourier transform. The output is in Fourier. Omega amplitude Okay, so this is an example how to this is the process how to transform from time domain to frequency domain. Okay, in reality there is no sinusoidal all the time. There is not sinusoidal all the time. Some of the signal they have exponential sign, for example like this, exponential sign, or like this, exponential sign. Okay, to consider this type of sign, exponential sign, we need to add here with exponential graph. When we time this exponential graph here, let's say this graph is e minus sigma. Let's say this is minus sigma t. So what we get is minus infinity ft times e minus j omega t times e minus alpha t dt. Okay, now we can combine this, become times okay, we just combine it, can get dt. Okay, this part we can split into s, which is s equal to omega plus j sigma plus j omega. So final equation will become minus infinity ft times e minus st dt. This is we call, okay, due to s domain. So s domain is function for Laplace transform. Laplace transform is we transform time domain into complex frequency domain. Okay, S, complex frequency domain. This is complex number, so we call complex frequency domain. To view it graphically, what you can see is time domain signal, so frequency domain signal. Let's see our frequency domain is like this. Okay, this is our omega 1, omega 2, this is omega is this. Okay, frequency response, this is a frequency domain. So when we use from this one, we use Fourier Transform, we will get this kind of graph. Okay, if we use Laplace transform, okay, from this graph we can convert it into 3D graph. Okay, like this. Okay, same omega. Now this is okay, omega. Then we add one more axis. This is real axis. Okay, because we have complex number sigma plus j omega. So now this axis will become j omega, imaginary axis, and this is sigma or real. This is imaginary. Here is real axis. So S equal to sigma plus j omega. This is complex number. Okay, for this Fourier, for this frequency response. So this is the view from Laplace transform view. Okay, by using Laplace transform, we can convert time domain graph into frequency domain graph in complex number. Okay, we have this axis, real axis, and also imaginary axis. For example, let's say our sigma is equal to -1, so our graph will be here, -1. So we can move graph to real axis. For example, and then let's say our sigma is +1, so graph will be here, +1. So we can moving at this axis. And also, if our sigma is equal to 0, means that S equal to j omega. When S equal to j omega, okay, from the general graph, when S equal to j omega, this one is equal to j omega, we can see that this equation also valid for Fourier transform. Okay, same equation for Fourier transform. Okay, so the graph will be at the 0 axis, as a real equal to 0. That's why we call Laplace transform is also called as generalized Fourier transform. When we look at time domain graph, we know that time domain graph consists of a few signal, a fundamental signal, an unwanted signal, or harmonic signal, noise signal. There are a lot of signal consist in time domain graph, combination of a few signal. So in order to remove all the unwanted signal we must convert it into frequency domain. So by using Fourier transform or Laplace transform, we can convert it into frequency domain. So we can separate it in a few numbers of signal. Let's say, for example, this one is consist of frequency 1, this is frequency 2, and so on, frequency 3, frequency 4, and so on. Okay, in order to remove all this, all the unwanted signal, we can use a filter. For example, we want to our fundamental, let's say for our fundamental is frequency number 1, so we just need this frequency and we don't want all this frequency. We can use filter window here, filter. So we can design a filter that this filter it will allow, let's say low pass filter. Okay, this filter will allow signal at frequency 1 only pass through it. Okay, when we use filter, our output will become W1 only. Okay, W1. All this W2, W3, and W4 will be eliminated. Okay, this is the application of filter. Then when we convert back into time domain graph, our signal will be smooth. For example, like this. Okay, compared to previous one, there is constant of noise. So our new graph will be filtered. This is we call filtered signal. Filtered signal. So we remove all the unwanted signal. Okay, this is one of application of frequency domain. The next application is, we know that in complex frequency we have sigma. Okay, sigma. So by using this sigma, we can move our graph, our response here, or here. So by moving this response along real axis, we can modify the bandwidth, this bandwidth. So we can modify it, increase or decrease the bandwidth, the bandwidth of filter. Okay, this is one example. This is two example of frequency domain. Okay, I think that's all for transformation of time domain into frequency domain. Okay, thank you. Bye.